In today's video, we are going to be investigating a closed water-air system and calculating the value of some of its parameters in a given scenario. So let's say we have a container with 1 kilogram of liquid water in it with air in the remaining space at an initial pressure of 101,325 pascals. The total volume of the container is 0.1 cubic meters at an initial temperature of 298 Kelvin. The container is closed, so air leakage is negligible. So given this information, are we able to calculate the final temperature that the container needs to reach in order to have a final pressure of 200,000 pascals? Yes, we definitely are, and I'm going to show you how. So when we approach this scenario, we have to consider and acknowledge all parts of the system. But since we're not considering factors such as the material of the container, the surrounding environment, and air leakage, like I said, et cetera, we know that the main two parts of this system are air and water. So if we want the container to reach a total or a final pressure of 200,000 pascals, we have to know that the total initial pressure of the container is equal to the partial pressure of the water vapor plus the partial pressure of the air. In my last video, we went over how the Antoine equation can be used to calculate the value of the vapor pressure of water at any given temperature. But we are going to be coding this problem in Colaboratory using Python, so we're not going to need to do this calculation by hand. We are set there. As for the partial pressure of air, we are going to be using the ideal gas law, which is PV is equal to nRT. And we are able to rearrange this equation to solve for the partial pressure of air, which will give us the moles of air times the ideal gas constant times the initial temperature divided by the volume of the vapor phase. And we can simply refer to it as the vapor phase because we have liquid water in a closed container, and once that water starts to evaporate, it goes from a liquid state to a gaseous state, thus the vapor phase. And we need to list what our ideal gas constant is equal to, and we know that it is 8.314 joules per mole Kelvin. So now we have to calculate the volume of the vapor phase. The volume of the vapor phase is equal to the total volume of the container minus the volume of liquid water. But we don't know the volume of liquid water. We do know the mass of the water, and we also know the density of the water. We know that the density of the water is 1,000 kilograms per cubic meter. And we also know that the formula for density is mass divided by volume. And since we have the mass and the density, we can rearrange the density equation to solve for the volume of the liquid water. Which will give us the mass of the water divided by the density of water. So now that that's done, one more thing that we have to do before calculating the final temperature is figuring out how many moles of air are in the container. But if you remember, the system is closed. The container is closed. There is no air leakage, which means that the amount of moles in the beginning is going to be the same all the way through until the end. The moles are simply going to stay the same. And since we have the initial pressure equation, we can basically say that it is pretty much the same as the final pressure equation with the substitution of some of our variables. And so we can take this equation and rearrange it to solve for the moles of air. So I just rewrote this equation and substituted the initial gas law that we set equal for the partial pressure of air, and simply inputted where our partial pressure of air variable was. And now I'm going to rearrange it for the moles of air. And so we get that the moles of air in the container is equal to the initial pressure minus the partial pressure of water times the volume of the vapor phase divided by the ideal gas constant times the initial temperature. But as I said, our final pressure equation is pretty much identical to our initial pressure equation. But all we have to do is swap out the initial pressure and temperature variables for the final pressure and temperature variables. So we can rewrite this equation as the final pressure minus the partial pressure of water times the volume of the vapor phase divided by the ideal gas constant times our final temperature. And with all of this work we have done, we are now able to calculate what the final temperature would need to be for the container to reach a final pressure of 200,000 pascals.
So as I mentioned before, we're going to be coding this problem in Colab, and the first thing that I'm going to do is run this cell with preloaded code into it. And what this code is going to do is going to download files from GitHub that contains various property data for a numerous amount of compounds, chemical compounds. And we are going to take a look at that data. So as you can see, there are a plethora of different compounds to choose from, but we are interested in water, so I'll go ahead and open up the file for that. And this file contains things such as the critical temperature, melting point, boiling point, heat of vaporization, specific gravity, liquid density, etc., etc. A lot of things that can be useful for problems like this. So in order to actually be able to implement these properties into our code, I'm going to import tools.che as CHE. And then we are going to want to set a variable that will allow us to actually call forth those properties into the code. And I will call that variable P. And so then I'll do che.props. And we have to input the compound that we want the properties for. And as I mentioned, we really want those properties for water. So after this, we can go ahead and set up our variables and their values. And I'm going to label this section the parameters for part A, because there is going to be a part B. And so we can go ahead and start naming our variables with their respective values. So we know that the total volume of the container is 0.1 cubic meters. The initial pressure is 101,325 pascals. The initial temperature is 298 kelvins. The mass of the water is 1 kilogram. And the final pressure of the container is 200,000 pascals, but I will do 2E5 or 2 times 10 to the 5th. And we cannot forget to include the ideal gas constant, which is R is equal to 8.314 in joules per mole Kelvin. So another really important thing that we want to do is calculate the density of liquid water. And to do that, I will do P dot rho L, rho being the variable for density, and L meaning that we want the density for the liquid state of our compound. And we want to find that density of the liquid state at the initial temperature. And so it's saying that the density for liquid water at our initial temperature will be 995 kilogram per cubic meter, which is not that far from what I stated the density of water was, which was 1,000 kilograms per cubic meter. So I have no worries, that is perfectly fine. And it's at a higher accuracy, so we will be okay with that. And so before we can calculate our final temperature, we need to calculate how many moles are in the container. And we know that to be the initial pressure minus the partial pressure of water, which will do PVAP for vapor pressure at the initial temperature, times the volume of the vapor phase, which is the total volume of the container, minus the volume of liquid water, which is the mass of water divided by the density at the initial temperature, divided by the ideal gas constant times the initial temperature. And we can see how many moles are in the container, and it's giving us a value of 3.92 moles. So now that we have that, we can actually start to calculate our final temperature. And in order to do that, we're going to need to implement the root solver into our code. And we're going to use a root solver from SciPy Optimize. It will take the root of a vector function or our nonlinear equation that we made by simply taking our final pressure equation and subtracting the final pressure from both sides and allowing us to set the entire equation equal to 0. So I'm going to do from SciPy Optimize and import root. So as I mentioned, the root solver is going to find the root of our equation and solve for our unknown parameters, which in this case is the final temperature. So we have to define our function that I'm going to call simply pressure equation. And this function is going to take in a vector, which I'm going to call v. And so the vector is going to contain a single value because we only have one unknown parameter in this scenario, which is our final temperature. So I will set that equal to the first element of our vector. So at this point, we're going to want to break up our final pressure equation into smaller parts. And I'm going to start with the partial pressure of water. And we're going to take this at the final temperature. And I'm also going to label what each part of the equation is, just so we're aware and understanding of the entire equation. Next, I'm going to write the equation for the volume of the vapor phase. And finally, we're going to write the equation for the partial pressure of air. So just to recap, our partial pressure of water is just simply the vapor pressure calculation at the final temperature. The volume of our vapor phase is the total volume of the container minus the volume of the liquid water, and the partial pressure of air is equal to the moles of air times the ideal gas constant times the final temperature divided by the volume of the vapor phase. And so now we have to return the equation that we originally started with. And like I said, we subtracted the final pressure from both sides and set it equal to 0. So our equation is the partial pressure of water plus the partial pressure of air minus the final pressure. So now we can actually put our equation into the root solver. And for this root solver, we need an initial guess. So I'm going to use the initial temperature. I think that the temperature starts there, and so it can only deviate from that point. So why not? And we know it worked because the success is true, and we can also confirm this by taking notice of the solution causing the function to go to a value of negative 4.9 times 10 to the negative 10, which is essentially 0. So we have now figured out that if we want this closed water air system to reach a final pressure of 200,000 pascals, the final temperature has to be 366 Kelvin.
So now on to part B. So what if instead of the total volume of the container or the system being 0.1 cubic meters, instead it was unknown? And additionally, of the 1 kilogram of liquid water we started with, this time we wanted 0.3 moles of it to be water vapor. To absolve any confusion, for my variable, I did N for moles, sub W VAP, which stands for water vapor, and B for desired. So to approach this scenario, we are going to want to utilize some of the calculations that we did in part A. The first one being the volume of the vapor phase is equal to the total volume of the container minus the volume of liquid water. And we also know that the volume of liquid water is equal to the mass of water divided by the density of water. But in this case, we don't know the true mass of the water because 0.3 moles of it is water vapor. So in order to figure out what it actually is, we have to subtract the moles of water vapor from the total mass. And then from here, we have to recognize that our units are not consistent at all. But we can get them to be in kilograms, which is what our math started at, by multiplying the moles of water vapor by the molecular weight of water. And then seeing that we're a step closer, but still not quite there yet because this is in grams. So to get in kilograms, we'll simply divide it by 1,000 since that is the conversion for grams to kilograms. And now we've successfully gotten it into kilograms, so all of our units are consistent, and we're able to divide this entire expression by the density of water. So from here, we'll also want to be able to calculate the moles of water vapor that we desire, and we can use our ideal gas law. Where the the partial pressure of water times the volume of the vapor phase is equal to the moles of water vapor that we desired times the ideal gas constant times the final temperature. And we can go ahead and rearrange this to solve explicitly for the moles of water vapor desired.
So coming back to Colab, all we really have to do is modify some of the code that we created for part A and make it relate to the current scenario that we have in part B. And the first thing that we're going to want to do is create our variable for the moles of water vapor desired. And I'm going to label this section as parameters for part B, even though it's just one new parameter. And we know that that was equal to 0.3 moles. And next we can copy and paste this chunk of code and begin to alter it so it fits the parameters for part B. So we're definitely going to want to change pressure equation to something else, and to be simplistic and, just straightforward as I always am, I'm just going to change it from pressure equation to pressure equation 2. We'll keep the name for the vector the same, but one thing that we want to make sure that we do is include our second unknown parameter, which in this case is the total volume of the container. And we're going to set that equal to the second element of our vector. And the reason why it has two elements is because there's two unknown parameters, as opposed to in part A, there was only one unknown parameter, so our vector only had one value in it. So we're going to set that equal to the second element of our vector. And now we have to modify some of these equations and add some new ones. So the equation for the partial pressure of water can stay the same. We're going to want to come up here a little bit and copy and paste the equation for the moles of air and label it. And then next we have to change our equation for the volume of the vapor phase, because we knew that with 0.3 moles of water vapor desired, we had to subtract that from the initial mass of water that we started with. And then multiply it by the molecular weight of water. And so it's worth mentioning that when we do this calculation in Python, I am personally going to use the property function to take the molecular weight of the compound that we chose, which was water. And so we're going to do this because, say, for instance, in the future, you want to, come back to this problem and change the compound that you're taking the properties of to apply to this problem. Say if, instead of me taking the property of the molecular weight, or the property of water, which was the molecular weight, I instead input the actual value for the molecular weight of water, which is 18.02 grams per mole. Now, if I did that and, at a later time came back and decided I wanted a different compound, well, I would have to come back down to this part of the code and delete the molecular weight for water and then input the molecular weight for whatever new compound that I picked. And that just really decreases the effectiveness and the efficientness, and the fluidity and versatility of our code. So instead of doing that, we can just take the properties of whatever compound we pick, and it'll automatically sort through the files of our property data and find it and input it, and it'll apply to any compound that we choose. So, as engineers, we want to work smarter, not harder. And that's a feature that I would really recommend you using for, coding a problem like this. And so we also have to remember to divide that by 1,000 in order to convert grams into kilograms. And we can keep the density of water at the final temperature the same. We can also leave the partial pressure of air, but we do have to input our equation for the moles of water vapor, which will be equal to the partial pressure of water times the volume of the vapor phase divided by the ideal gas constant times the final temperature. And so finally, in the last problem where we only had one equation, one unknown, we only returned a single equation, but since we have two, we have to return both of those. And our second equation is going to be the moles of water vapor minus the moles of water vapor desired. And set that equal to 0. And the reason we're able to do this is because, well, the moles of water vapor in the container is going to be equal to the moles of water vapor that we want. So we can subtract either term from both sides, whichever we decide to choose, because there's only one term on each side, and set that equal to 0, and that will be our second nonlinear equation. So we're coming to the end of the road. We only have a few steps left. All we really have to do at this point is input our equation into the root solver. And we have to supply our two initial guesses for these unknown parameters. So for the temperature value, I'm simply going to stick with what I did last time and assume the initial temperature that we started with at the beginning of the problem. And for the total volume guess, I will pick the total volume of the container in part A, which was 0.1 cubic meters. Sorry, you do not need to input the units to the root solver. But unfortunately, we can't get everything right the first time, but that's okay. We will work around this. So it didn't work. The success was false. The iteration is not making good progress, and the solutions made the function go to values of -46 and -5. That's not close enough to 0 for us. So basically what we're going to want to do is make some better initial guesses. And to do this, instead of using the initial temperature that we started with, I'm going to instead use the final temperature that we received in part A, which was 366 Kelvin. Now for the total volume of the container, we can actually kind of calculate it using the equation for the moles of water vapor that we have up here. So when we look at that equation, you'll notice that, our nonlinear equation, as I said, is the moles of water vapor minus the moles of water vapor that we desired because, or equal to 0, because they're equal to each other. So knowing that, we can say that the moles of water vapor is simply 0.3 moles. Now, we know the partial pressure of water, we know the ideal gas constant, and since we are assuming that the final temperature is 366 Kelvin, we can input that in this equation. So the only thing that's really left to solve for is the volume of the vapor phase. Now, we also know that the total volume of the container is equal to the volume of the vapor phase plus the volume of liquid water, which we can also solve for by taking the mass of water divided by the density of water at our final temperature of 366 Kelvin. So we can actually kind of calculate the total volume of the container and create a better initial guess for our root solver. So I'm going to go ahead and do that to rearrange the equation for the moles of water vapor to explicitly solve for the volume of the vapor phase instead. And that will give us the moles of water vapor desired times the ideal gas constant times our final temperature, which we're saying is 366, divided by the partial pressure of water at our initial temperature of 366 kelvins. And so, yeah, we can see that the volume of the vapor phase with these conditions is 0.01 cubic meters. So now all we have to do is input the equation for the total volume of the container. And like I said, take the mass of the water and divide it by the density of the water at our assumed final temperature of 366 Kelvin, which will give us that the total volume of the container is 0.012 cubic meters. And so it's not that big of a change from the volume of the vapor phase, but we are fine with that, and we can go ahead and change our guesses to 366 and 0.01. And thankfully, this time around, it worked. All we had to do was work out a couple of kinks, but our success is true. The solution converged. Our function reached values of 6.14 times 10 to the negative 6 and 2.38 times 10 to the negative 10, which is way better than negative 46 and negative 5. So we know that, under most of the same initial conditions given in part A, except for us wanting 0.3 moles of water vapor to be desired in this specific scenario. With that, the total volume of the container will end up being 0.01 cubic meters. And in order for a container with that volume to reach a total pressure of 200,000 pascals, it has to be raised to a temperature of 366 Kelvin. So thank you guys so much for joining me in creating nonlinear equations derived from the ideal gas law and using a root solver in Python to find the roots of those equations, which doubled as the values of our unknown parameters within a closed water air system. I really hope you enjoyed this video, and I'll see you in the next one. Bye.